Okay, this is where we left off in the last video. Um, and I'm talking about the central limit theorem. It's not a central limit theory, by the way. Please, make the distinction here. It's central limit theorem, CLT. You'll see people use that term. And the central limit theorem has two parts to it, okay? And if you understand the symbols here, this becomes your cheat sheet, okay? This becomes your cheat sheet in a way. And you don't have to memorize this. I will give you these formulas on the exam, okay? I'll give you the formulas on the exam. And what is the central limit theorem? Two components, okay? Listen carefully. I will repeat it. Hopefully you write it down. If you try to memorize these words, I'm going to tell you you're likely to get it wrong on the exam. Because what you need to do is understand the concept, and I'm assuming then you can generate the words to describe it, okay? Otherwise, you can really screw things up. Well, what is this symbol? This is the mean of all the means. S, the mean of a bunch of means, like this. I'm plotting the means, right? These are M's now. These are means of samples instead of X values, right? These are means of samples. Same thing all the way along. This is the overall average, the overall mean for this group of sample means. That's what this is. Central limit theorem, what we developed in the last video, and that's why I took so much time developing the concept. Central limit theorem describes the relationship that we see. This is real, folks. This is like the quincunx. You can do this on a computer generator as well, and you'll find that the mean of all the sample means in a distribution will be equal to the mean of the original population from which the samples were taken. Okay? And I did that grammatically correctly. I didn't leave the from at the end of the sentence, but I could do that if you want. It's easier sometimes for people to hear it. The mean of a distribution of sample means will be equal to the mean of the population that the samples came from. Okay? The standard deviation, here's the pattern. If we increase the size of the samples, not the number of samples, we're going to do 10,000 for each of these, okay? If we increase the size of the sample, what we find is the standard deviation of a distribution of sample means will be equal to standard deviation of the original population divided by the square root of the sample size. What this tells us is the standard deviation of a sampling distribution of sample means will get smaller as the sample size gets larger. Okay? The standard deviation of the sampling distribution of sample means will get smaller as the sample size gets larger. Okay? The size of our sample gets larger. All right, well, big fat deal, right? So why are we doing all this, Dr. Speck? This is, complicated. I'm like, yeah, it is, okay? It's increasing sample size, right? Well, if we know that this is true, and it absolutely is true, what does that imply for us? Well, let me ask you this question. I'm going to bring up the canvas bag one more time. If we wanted to know what was in this bag, do you think we would be better off taking one block out and make our guess? Or if we took 4 blocks out got the average of those 4 blocks and made my guess, or if I took 8 blocks out, or if I took 15 blocks out. What do you think you would be most confident making the guess if we took out a sample of 1 block, 4 blocks, 8 blocks, or 15 blocks? Yeah, I hope you would say, if I took out a sample of 15 blocks, I could make a better guess at what's in the bag than if I just took out 1 block. Okay? And in fact, that's what this is telling you. We still expect that the most common sample mean will be 14 or around 14. But what we're doing here, this is central limit theorem, 2 components. But this is really what's going to give us our power. It's telling us that the larger the sample size, the more likely the sample mean is going to be close to this, right? Which is this. Everybody follow the logic here? There's a couple of steps. If this gets smaller, if the standard deviation of my sample means comes inward, gets smaller, the standard deviation is smaller, less spread out, the larger my sample size, the more an individual M, an individual sample, the more likely it's going to be close to this. Okay? That means as we increase the size of our sample, our confidence that we're making a good guess increases because there's less variability. Okay? And in fact, this is called the standard deviation of a sampling distribution of sample means. If you want to make it shorter, good luck, because you shouldn't. This is the standard deviation of a sampling distribution of sample means. It's going to get smaller as my sample size increases. This is called regression to the mean. Regression, that is, things are regressing to the mean, okay? If that's the case, then I'm more confident with larger samples that my mean is going to be close to the overall mean, which is what I'm trying to guess. Okay? So this is called the standard deviation. This is called the standard deviation of a sampling distribution of sample means. What we see here is regression to the mean. This also has another name. It's called the standard error of the mean. Because when we do inferential statistics, what are we doing? We're making a guess. And when we make a guess, there's always room for error, is what people say. But we're going to be much more sort of specific about this. As we increase our sample size, we have less error in our guess, right? The samples are coming inward to the mean. Less error, less error, less error. The silly example that I used in the last video, if our population is 25 blocks and I take out all 25, what's my error in my guess? It's 0. I mean, if I have the entire population, I don't need to guess. I have it all. Everybody with me? That's why it was such a weird example. In normal circumstances, you never get the entire population, okay, when you're trying to make inferential statistics. And in fact, you've probably seen this before if you pay attention to the news at all, because when let me do this. If you look at political polls, you know, they'll say the president's approval rating is 48%, 2%. And then you'll see this, plus or minus 2%. You're like, what the hell does that mean? Well, this is their guess for what's happening in the population. That's their guess. But they're saying maybe plus or minus 2% because we could be wrong. Standard error of the mean. That's what this is, standard error of the mean. If they, this might be based on a political poll of 1,500 people, let's say. That would be the sample size. If they did, let's say, 5,000 people, they might report an approval rating of 48%, plus or minus 1%, right? And I'm just making this up. They're the people that do these polling. I mean, it's PhD level statisticians that are, really good at this stuff. So, this might be a sample of 1,500 people. This might be a sample of 5,000 people. Notice what happens. We're still going to make our guess for the overall approval, but look what's happened to our standard error. If I have a larger n, my standard error comes inward, right? So that I am more confident here than I am here because it's based on 5,000 versus 1,500. This is the standard error of the mean. You'll see that in polling numbers for sure, okay? The more you have, the lower your standard error, lower the standard deviation of the sampling distribution, and that relates to being confident. That relates to being confident. And that goes back to what I talked about in the last video. If you want to know what kind of a golfer I am, would you be more confident if you saw 10 of my games or if you saw 2 of my games? And I hope you would say, oh, I would be more confident if I saw 10 of your games. And that would be correct because this is going to go down. Okay? Now, it is true that I could go out and shoot my perfect average and then you would know how I played. But you still wouldn't be confident that that was the case. I mean, what we're doing here is, I told you what was in this bag and then we worked from there. But that was just to show you this pattern. But typically, you're not going to be shown what's in the population. That's your task, to infer, okay? Central limit theorem, here and here, okay? This is called the standard deviation of the sampling distribution of sample means. It's also called the standard error of the mean because it's related to making guesses, okay? And you can watch the previous video again if you would like to make sure you get this concept down because it is complex. And I don't know how people learn it or teach it without actually having that low-tech canvas bag and doing something to show how that works. By the way, can we go back and think about Bob? Remember Bob in the reaction time test? And I ask you, do you think Bob is intoxicated or not? And Bob had a reaction time, if I recall correctly, a reaction time of 337 milliseconds. And we made the guess that Bob was intoxicated because, for good reason. It's because this represented a very large z-score. And so we said, something weird's going on. I would be much more confident in making a judgment about Bob if I saw maybe, 5 reaction time tests. Sorry about that, folks. If I did 5 reaction time tests rather than just 1. And Bob might be, clamoring that, hey, I wasn't paying attention or, whatever it is. If Bob's reaction times look like this, I'd be like, wow, you know what, Bob? that ended up being a good guess because it matches the rest of your reaction times. If Bob's reaction time looked like this, I'd be like, wow, okay, that was an outlier. That was something weird that was happening with Bob. And so it's a good thing we have this. And now I have, if I did the mean for all 5 of these, I would be more confident in my guess. Okay? This is how it works. So you're less likely to be, you might have an aberrant score, but if I look at 5 of your scores, it's difficult to argue it's aberrant if the other scores are like what you had. It's just like sometimes students will come in and take an exam and not do well, and they'll come in and say, Dr. Speck, this is not like I usually do, and it doesn't represent how much I know this stuff. I never argue with students because I don't know how much they've mastered it. That's why you give multiple exams. Multiple exams increase your sample size. If you end up failing every exam, it becomes harder for you to argue that you know the material. Now, of course, the other predicament I don't hear much of, rarely do I hear someone come into my office and say, Dr. Speck, I got an A and I don't usually do that well. Well, of course you're not going to say that, right? But you may get an A and then end up getting, a couple of C's. And your average is usually more indicative, the more, the more numbers that I have in the sample, the larger the sample is, right? It gives me a more confidence, okay? And by the way, you will typically, when I say regression to the mean, I have a certain golf ability. And even though I may go out and have a really bad game one day, the following round of golf, I'll probably be closer to my average. Or if I have a really good game, like, wow, I just shot the best round I ever shot. If I go out and play 4 more rounds, it's likely that my overall average will be back to kind of what's normal for me, okay? And regression to the mean is also, I like to use real life examples as well, always, because it's real life. Mathematics is describing real life, not something different than that. It's just we're formalizing and being more sophisticated and specific about this. I always tell people regression to the mean is why it's more difficult to find a really, really good sports team than it is to find a superstar athlete, okay? We'll go back to LeBron James. I saw him play a few years ago at Madison Square Garden, and it was just phenomenal. It was unbelievable. As a statistician, I was really quite blown away because these are all professional basketball players, right? But when LeBron James steps on the court, it's like a whole new game. It was really wild. But notice, so LeBron James is far out, man. LeBron James is out there. Large Z-score, right? But what happens is LeBron James has to play with 4 other basketball players, right? It's a 5-person team. So in a way, one way you can think about this is instead of LeBron James, right, n equals 1, we have LeBron James plus 4 other players, n equals 5. And so even though, let me put it this way, right? Here's LeBron James. So LeBron James is out there, but he's got to play with 4 other players who might be good, right? Above average, maybe one at round average or maybe below average, okay? So that the team is taking these 5 performances together and getting the mean for those 5 performances. The average for the team, the performance for the team, is never going to be as extreme as LeBron James is. If we think about the canvas bag, and by the way, folks, you can't do well in this course without sometimes just sitting and sort of thinking this through and scratching your head and thinking a little bit more. Ask me questions if you have them. Okay, this is not, once again, this is not just like the capital of, Ohio. What is the capital of Ohio? Is it Columbus? I think it's Columbus. It's just a fact you know or you don't. This is stuff that's more complex. I know it. That's why I love it. But sometimes people use the wrong strategy. Like you think you're going to get it just by reading it or hearing about it. You really have to think it through, okay? If we go back to our canvas bag, remember, if we took out one block, we could get an 18, like a LeBron James. If we took out one block, we could get a 10. But as soon as we took out more than one block, those extreme blocks have to be sort of added together with less extremes, and so those come in. So LeBron James, a little bit frustrating, right? Because he's really good. He's got to play with these other folks, brings the team average closer to the overall NBA. If this is the overall NBA, here we go. Not so good for LeBron James. For the worst player in the league, because regression goes both ways. It comes inward to the mean. Here's the worst player in the league. And the worst player in the league also plays with other players. And so the mean for that team is never going to be as bad as the worst player. The mean for LeBron James' team, never going to be as good as the best player. Things come inward. This is why it's more difficult to find a superstar team than it is to find a superstar individual, because it's regression to the mean. Okay? So let me do an example here. Let me do an example and show you how this works. Let's go back to IQ, something that we worked with before. Okay? And I said, we look at individual scores. The mean for these scores is 100. The standard deviation is 15, right? And so let me ask you this question. What is the probability, what's the probability that we would get an X value that was above 110? Okay? That's what percentage of the population scores above 110? Well, here's what we're talking about, right? Here's what we're talking about. Right here is what I want. You guys know how to do this. This is straight up z-scores, right? So if I get my z for 110, which is 0.67, how did I do that so quickly? Well, let's do this. Z here equals x minus mu over standard deviation. Z equals 110 minus 100 over 15. 10 over 15, 0.67. Okay? So if I go to my unit normal table, where is my unit normal table? Hold on a minute. It's over on the other chair. 0.67. My z-score of 0.67. So then I want to know how much is in the tail. How much is in the tail? 0.67, how much is in the tail? 25.14%. Okay. So, I mean, that's pretty high. About a quarter of the population has an IQ above 110. All right? This should be review. But now what I want you to do is, using IQ scores, what is the probability that we would get a group of, let's say, 6 people whose average IQ is 110. We're going to get a group of 6 people whose average IQ is 110. And here I want to take just a random sample. Okay, I'm not going to, an Ivy League school or Mensa Club or anything like that. So what is the probability of having a sample of n equals 6 where the mean for that sample is greater than 110? Okay, everybody with me? That's the question. Well, we have to use the central limit theorem here. And let's think this through. We know that samples of 6 are going to regress to the mean. That is, the variability of a distribution of samples of n equals 6 is going to have less variability. We know that because of the central limit theorem. Okay, so here's what we're going to do. I'm going to do this little thing like this that I like to do. I need to use my central limit theorem to say, well, what would samples of 6 look like? What would samples of 6 look like? Okay. And I know that it's going to be less variable than this. We can draw that. I know that this distribution, that the mean of all the sample means is going to be equal to this. How do I know that? From my central limit theorem. So here we go. Okay. So far, so good. And I know that the standard deviation for this distribution is going to be equal to the original standard deviation divided by the square root of n. Well, I have the original standard deviation, 15 divided by the square root of 6. So let's do that, okay? Square root of 6, 2.45. So 15 divided by 2.45, 6.12. 6.12. Okay? Now, the question here is my mean of 110, because I want to know what's the probability that I'm going to get a sample of 6 people whose IQ, the average for the group, is greater than 110. So this is what I'm looking at here. Okay. I want you to guess about what the answer will look like. Is there going to be fewer people in the extreme and more in the center, or fewer people in the center and more in the extreme? Well, if this is the picture, we know that the standard deviation is going to get smaller. So that means more people are going to be closer to the mean. So fewer people are going to be in the extremes. So let's do the computations. Here's the z-score formula I used here. The x value, how far away from the mean it was, and we're going to divide by standard deviation, right? Review, 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 okay? For this distribution, we're going to, I'm going to erase this now. We're going to use the z-score formula. It's the same logic. We're going to use the z-score table. It's the same logic. But we're going to change this up a little bit. We're going to say, how far is the mean that I'm talking about? How far is that from the mean of all the means? And then I'm going to divide by the standard deviation of all the means. Sometimes this blows people's mind. I say, this is the same formula as this. Like, whoa, no, it's a different formula. It's a different formula. Well, it's different symbols. Here I'm saying, how far is this x score from the mean? And I want to put it in terms of the variability. Here I'm saying, because these are m's, how far is the m away from the mean for the m divided by the standard deviation for the m? We're just ming it up, m and m, m and m, m and m, okay? But it's the same concept. So here we go. 110 minus 100 divided by 6.12. It's the same distance away from the mean. It's 10 points away from the mean. But because the variability is smaller, it effectively means they're further out. Not in terms of points, but in terms of the people that are beyond them and people that are below. So let's do this. 110 minus 100 divided by 6.12. So our new z-score here, 1.63. I'm going to use my z-score table. I want to know what proportion of people are beyond that. And here, 5.16%. It's far less probable to get 6 people taken at random with an IQ above 110 compared to a single individual with an IQ above 110. Once again, this is like the little LeBron James example. It's not that rare to find a person with a high IQ above 110. If I'm looking at a random sample of people, their average has to be above 110. That doesn't happen very often because a lot of times you're going to get people around the average. A lot of times. So you got 6 people, 4 of them are around the average, one of them's really out there. They're going to regress to the mean, okay? It's much less likely to get 6 people whose average IQ is above 110 than to get a single individual whose IQ is above 110. Same thing works on the other end, and maybe you can do this for practice. What is the probability that you're going to find someone with an IQ below 85, let's say? Okay, figure that out. Below 85. What's the probability that you're going to get a group of 6 people, taken at random, with an IQ below 85? What you'll find is you're going to find people with IQs below 85. Not many, but there will be some. To get 6 people with an IQ below 85 it's very rare. Okay? So, very important. Last video and this video, the previous video and this video, extremely important. We need that tool to go forward. And the next video, we're going to be strong into inferential statistics, and we're going to start doing research, using research examples. We have now all the building blocks. This was our transition from z-scores and descriptive statistics to probabilities, predictions, and making guesses for inferential statistics. Very exciting and very powerful. We've got to know the central limit theorem, though. And so we'll do some hypothesis testing in the next video.